Okay, as I said before, I'm just tracking these AI applications for weather and climate forecasts. I am not at all an expert on AI, so many of the details, technical details of these papers are not going to be covered by me, but I want to track them because they are becoming a bigger and bigger part of our business, and they will continue to be so. As we said before, AI is going to help us improve the dynamic models for forecasts and also directly make forecasts by itself. So models will do forecasts. AI forecasts directly are being made, so we have to track them just to be aware of what's happening. So this is a paper that came out I think a few months ago, machine learning model that outperforms conventional global seasonal forecast models. So this has got some special technique they developed to make forecasts similar to dynamic models, and we'll see what it is and why that is important. Skillful subseasonal forecasts are crucial for various sectors of society but pose a grand scientific challenge. Subseasonal are the time scales beyond weather and shorter than a season, subseasonal, so less than 90 days, let's say. And they are very important because there is also predictability in them, and they are very useful for many things like farming and water resource planning, energy, etc., etc. I have a full course on subseasonal forecasts and applications if you want to follow up. Recently, machine learning based weather forecasting models outperformed the most successful numerical weather predictions generated by the European Centre for Medium Range Weather Forecasts, which is one of the gold standards at present, but they have not yet surpassed conventional models at subseasonal timescales. So this is a new timescale where it's being tried and seems to be doing better than dynamic models. This paper introduces Fuxi seasonal to subseasonal, so Fuxi S2S, a machine learning model that provides global daily mean forecasts up to 42 days, encompassing 5 upper air atmospheric variables at 13 pressure levels and 11 surface variables. So many details there, but basically when we say up to 42 days, that's where the subseasonal forecast comes from. So weather forecasts are typically out to few days, and they are initialized models, and there are many details, and we know that weather goes chaotic after a few days. Small errors in the initial conditions produce a large errors in a few days, but you have predictability at longer than a few days because of various physics which has memory, let's say. So without going into those details, just remember that going beyond weather forecast. So you have short term, 1 to 3 days, medium term, let's say days 3 to 10, and then you have extended range, which goes from weeks 2 to 4 typically. So we are in that range here, subseasonal time scale. Okay, so the test is always on how well you do with surface variables, because that's what we are often looking for in terms of applications for farming and health and energy, etc., as I said already. Okay, so Fuxi S2S trained on 72 years of daily statistics from ECMWF ERA 5 reanalysis data, outperforms the ECMWF's state-of-the-art subseasonal to seasonal model in ensemble mean and ensemble forecasts for total precipitation and outgoing long-wave radiation, notably enhancing global precipitation forecasts. So precipitation is a key variable for many applications, water and agriculture, of course, and everybody looks for good precipitation forecasts, and dynamic models have issues because modeling precipitation is a difficult challenge. We've discussed this elsewhere. The improved performance of Fuxi S2S can be primarily attributed to its superior capability to capture forecast uncertainty and accurately predict the Madden-Julian oscillation, one of the subseasonal modes of variability, extending the skillful MJO prediction from 30 days to 36 days. Moreover, Fuxi S2S not only captures realistic teleconnections associated with the MJO, but also emerges as a valuable tool for discovering precursor signals, offering researchers insights and potentially establishing a new paradigm in our system science approach. Well, as we said, AI is being used to improve the processes, which would even improve things like MJOs in dynamic models. Van-Julian oscillation is an intraseasonal timescale phenomenon that's well known, and there is some predictability in it. So can we just use data, which is ECMWF era 5 reanalysis, which is a combination of a model and data, to fill the gaps to produce gridded continuous data sets, which can then be used to train a machine learning model to do forecasts. Okay, should I read so many details? Let's read a bit, because we need to provide some details on what is being done, especially in terms of ensembling, and that's a critical progress here. Developing an ensemble prediction system, EPS, based on traditional physics-based numerical weather prediction models is a widely acknowledged and effective method for enhancing subseasonal forecast accuracy. Ensembles basically means we do multiple realizations, because Mother Nature provides you one integration forward from today to tomorrow, let's say, but we cannot exactly capture this, and Mother Nature has many possibilities out of which she picks one for whatever reason. So doing ensembling basically means we cover the possibilities of what Mother Nature could have done and could do in the next let's say 42 days, and we do ensembles to say what are the range of possibilities that are going to occur in the next 42 days in this case. Major forecasting centers have implemented such EPS for subseasonal forecasts. However, these systems often exhibit considerable biases, particularly in predicting extreme events. The two primary challenges in this field are ensuring an adequate ensemble size within computational constraints and designing ensemble perturbations that accurately reflect uncertainty in key atmospheric and oceanic variability. Enlarging the ensemble size is beneficial for forecast performance, but the substantial computational costs typically limit the ensemble sizes to between 4 and 51 members across 11 international forecasting centers. That's a very specific number, but basically when you say you want to give a range of possibilities that can emerge in the next few days or few weeks, then how many members of simulations, how many samples do you want to produce? It's a big field to discuss how many we need to be realistic and so on, but there is always a limitation of how many you can do, because it takes a lot of computing power, and AI can overcome all these, not only do these things faster, but also computationally much more efficient. Given these computational limitations, machine learning models emerges as a promising alternative for direct subseasonal forecasting. Machine learning models have the advantages of significantly higher computational efficiency, facilitating the generation of a large number of ensemble members, which are crucial for prediction skill and reliability. Recent advancements in machine learning for medium-range weather forecasting have demonstrated that machine learning models can outperform the high-resolution forecasts, HRES, generated by the European ECMWF, widely considered as the most accurate global weather forecasts. Remarkably, so I'll jump ahead and see what specifically has been done in Fushi S2S. Remarkably, Fushi S2S outperforms the ECMWF subseasonal to seasonal S2S ensemble, which is recognized as the most skillful S2S modeling system in producing both the ensemble mean and probabilistic forecasts. So probabilistic is the spread of the ensembles, and ensemble mean kind of tells you what is the most likely state, let's say. Its efficacy is particularly evident in extreme total precipitation forecasting, as exemplified by its accurate forecast for the 2022 Pakistan floods, which basically drowned the entire country. Such capability is closely related to Fushi S2S's improved prediction of the Van-Julian oscillation, MJO, a key driver of global climate patterns, extending the skillful MJO prediction from 30 days to 36 days. Well, MJO is not a key driver of climate patterns, but it's a key member that has impacts on day-to-day weather, as well as it can affect lower frequencies like El Nino and so on. And El Nino, of course, has global teleconnection, so MJO is a key part of the global weather and climate. These results further confirm that the notable improvement in Fuchs S2S's performance can be primarily attributed to the innovative perturbation module for ensemble generation. So in dynamic models, initial conditions are perturbed, or some other fancy methods are used to produce ensembles. So each integration is slightly different, and to see where it goes as you integrate forward. And in a machine learning method, you obviously have to figure out how you are going to generate these ensemble members. So the innovation is done in there. That's where the technical details are, which I'm going to skip, unfortunately, because I'm not an expert in that. And we don't necessarily need the details. We just need to understand what they are doing at some level of generality, right? So let's see, primarily attributed to the innovative perturbation module for ensemble generation. Another promising result is the ability of the Fuchs S2S model to identify potential precursor signals to physical processes. Beyond mere accuracy, in many applications involving machine learning forecasts, it's imperative to understand and validate the decision-making mechanisms of these models. Such understanding not only leads to enhanced trust in the model's predictions, but also increase the likelihood of implementing effective actions, particularly in mitigating the risks associated with these extreme events. So if people know the model is offering consistently skillful, reliable forecasts, then decisions will begin to be made based on those, because decisions often involve deploying resources, spending money, finding people at the right place at the right time, and so on. So they are not silly decisions at all, right? So recent developments in explainable machine learning XML methods have facilitated this interpretation. This study delves into the 2022 Pakistan floods, investigating the Fuchs S2S model's predictions to identify key geographic regions that significantly improve its predictive accuracy. This is achieved through the generation and analysis of salient maps, wherein the identified regions in close alignment with the insights from previous studies. Therefore, we argue that Fuchs S2S transcends traditional NWP models in terms of accuracy and speed, potentially unveiling previously unrecognized processes within Earth system in subseasonal forecasting. So, if machine learning model does consistently better, then you can go back and try to understand why that is, right? That may help you improve the process understanding in the dynamic system, and use that to improve predictions in the dynamic systems. So right now it's not really clear whether AI will completely replace dynamic models. That's pretty much not going to happen. So it's a matter of how we will combine dynamic models and AI to get better predictions at all time scales. So improving dynamics always is a key aspect of using AI as well, right? So this is an example, jumping ahead. Comparison of globally average and latitude weighted temporal anomaly correlation coefficient of the ensemble mean between ECMWF S2S forecasts in blue and Fuchs S2S forecasts in red for total precipitation, 2 meter temperature, geopotential at 500 hectopascal, and outgoing long wave radiations. If these dynamic quantities don't make sense to you, you can follow up on my other podcasts. So TCC, the temporal anomaly correlation coefficient, is a measure of skill, observations and forecasts. So you can see that for all these quantities, total precipitation, 2 meter temperature, geopotential at 500 hectopascal geopotential, and outgoing long wave radiation, the red lines are typically better than the blue lines pretty much everywhere, maybe not so much here. At some point beyond which you want to see if skill is being improved. So here you are in lead time in weeks. So 42 days is obviously beyond, it's in the range of 5 to 6 weeks. So total precipitation is better in the range of 5 to 6 weeks. Then you have to see if correlation is significant in terms of, let's say, explained variance in the rainfall. But if you are looking just for extreme events, then whatever reliable probability that is consistently being offered by a prediction can be useful. So everywhere, mostly the red bars are doing better. So Fuji S2S is doing better. Rows 1 and 2 represent the performance across these variables, utilizing all testing data from periods spanning from 2017 to 2021. A bootstrapping approach repeated 1,000 times is used for significance testing and so on. Basically, the main message is clear that the Fuji S2S is consistently beating the ECMWF dynamic S2S prediction models. Okay, this is further details looking at the global maps. Maps displaying the average ranked probability skill score RPSS, another measure, first and second rows here, and Breyer skill score, those details you can follow up, third and fourth rows, without latitude weighting. So you are looking at actual global maps, comparing ECMWF subseasonal to seasonal in the first column, Fuji in the second column, and the differences here. Okay, so you can see that the skill scores weeks 3 to 4, 5 to 6, this is for RPSS, and this is for Breyer skill score. Again, total precipitation 3 to 4, 5 to 6. Just look at the differences. Wherever there are red colors, basically Fuji S2S is beating ECMWF. Okay, is this important enough? There is a lot of patchiness. Obviously, precipitation itself is patchy, and mostly you care about land precipitation because we are not always worried about where it's raining on the ocean unless it's extreme events that ships want forecasts for, and so on and so forth. Always depends on the users, but land, there is always users who want it. So the main message is that S2S, again, globally the distribution shows that except for a few places where Fuji S2S is doing worse, which one has to read carefully, because on the maritime continent, Western Pacific into the monsoon region, generally there are reddish colors, but there are bluish colors. Are they systematically, is Fuji S2S systematically worse in the regions where there is not much rainfall, and then signal to noise ratio is small? Then we can ignore it. As long as it's doing well in the regions where there is a lot of rainfall and potential for extremes, we can take it, right? Another figure, I'm jumping ahead by a lot of text I'm skipping. Comparison of real-time multivariate Madden-Julian oscillation, which is a RMM, is a measure that Wheeler and Hendon index of multi-bull RMM. I always keep banking out on what it stands for. So again, we are looking at correlations now with lead times. You can see that ECMWF falls off in about 30 days, and Fuji S2S is extending it to 36 days in terms of the correlation being above 0.5, where it's considered useful. And then you can see some further details here in terms of lead time and how the correlation levels. So let's read exactly what we're looking at. Comparison of RMM bivariate correlation as a function of forecast lead times. Dashed black line signifies the prediction skill threshold of 0.5 correlation, and RMM bivariate correlation is depicted as a function of the month of the initialization. So here is the lead time, and depending on which month you're starting the forecast from, there are dynamic reasons why you may have things like spring predictability barrier, where the skill drops off because during spring the sun is crossing the equator. The system is not very strongly coupled. I don't know how to precisely explain it, but there is a lot of variability or noise in the system. So come in the winter, there is strong signal. Spring comes, everything begins to transition into summer. Summer has strong signal transitioning into fall and winter, but spring is noisier. So when you initialize the forecast does matter. So typically you can and it depends on which lead time you are looking at. So as lead time increases, you can see that the skill scores are lower anyway, keeping in mind the thresholds. But depending on when you initialize, you can have longer lead times with higher skill here in terms of correlation. Okay, so just try to get an intuitive sense. When you compare skills, you not only compare lead times but also see when the initialization is very important. If its skill drops off with initializing before spring, let's say any initialization before spring drops the skill consistently in terms of lead times, correlation may be high, but it's only good for a few days, let's say, not longer lead times. Then you have to worry about these things so that you know decision making can depend on where the skill drops off. Let me pause and get some water. Sorry about that. Okay, so sorry about that. Somehow this is January, almost end of January last week, and temperatures are still relatively mild in the morning and evening, but everybody on campus here at IIT and most of India are coughing because there is something in the air, maybe a bug going around. But nonetheless, coming back to the Fushi S2S model, this is a comparative analysis for the 2022 Pakistan floods prediction between ECMWF and Fushi S2S. As well as the precursor signals that contributed to the accurate prediction by the Fushi S2S models. In other words, you say Fushi is doing by ECMWF, and then you have to figure out why. What did Fushi see in integrating forward for predictions that ECMWF model may have missed? So that's where the process understanding from ML comes in. So jumping ahead without going into the details, standardized anomalies again, what the observation was and what ECMWF did with range. You can think of these as the ensemble spread, and what Fushi S2S did. So you can see that the Fushi S2S may have overestimated the anomaly, but nonetheless, if you look at the lead times, so let's make sure we are so this is the period of the flood observations, 816 to 831. So by 811 already Fushi S2S was saying something is going to happen, and 808 the signal was not so strong, but it was doing similar to ECMWF. But it had some precursor signals leading up to the flood period, so 721, 725, 728 and so on. So you can see what happened in the observations. Obviously observations are for the period where the flooding happened. So when you go back in time from the August flooding line to July few weeks before, you're trying to see what it is that Fushi saw that ECMWF didn't see. So 728 you can see that Fushi is seeing something in, let's make sure what the standardized anomaly, and it's understanding that some signal is coming that's potentially going to cause floods, and that's where its higher skill came from. So if you look at it in terms of spatial map, it began to identify, so that's the flooding region, and these are the combinations of sea surface temperature and total precipitation. So let's read, it's some probabilistic information there. Comparison of spatially and temporally averaged standardized total precipitation, anomaly of spatially and temporally averaged standardized total precipitation anomaly over the 2 weeks from August 16th to August 31st, 2022, showcasing the GPCP observations in black alongside the predictions from ECMWF and S2S real-time forecasts in blue, and Fushi S2S in red that I already explained here, and we are interested in the maps as to where the precursors are coming from. The black lines on the bar of ECMWF S2S and Fouché S2S forecast represent the 25th and 75th percentiles for comparison of temporally averaged standardized TP anomaly maps in B. The first column represents the GPCP observations, while the second and third columns display predictions from ECMWF and Fouché respectively, both initialized on July 28th. And the fourth and fifth columns correspond to predictions from ECMWF S2S and Fouché S2S, respectively, with an initialization date of July 21st. So this is initialized a few weeks before, and this is just a couple of weeks before. And you can see that here ECMWF saw something, and Fouché saw something. Maybe location-wise, this is better. Signal-wise, in standardized anomaly, this is stronger. In the 28th initialization, Fouché S2S is seeing something that ECMWF is basically not seeing in the standardized anomaly. And you can see again, 21, this is the flooding region, and what Fouché S2S is seeing, and what, 21 and 28 both are Fouché S2S. So once you convinced yourself that Fouché S2S saw something, I'm in the wrong, how did I'm going back in the wrong direction. Okay, Jesus, yeah. Sorry, it's morning and I'm a bit groggy because of this allergy-like thing. No excuse, I'm just not doing a good job, right? So, okay, I would just want to get the point about the precursors. So green contours indicate the borderline of Pakistan. Saliency map C were generated using the gradient of the negative standardized TP anomaly over the Pakistan region in relation to the input SST. Okay, so you have the conditional input of SST in relation to the Pakistan total rainfall. Okay, so let's just say that Fouché S2S saw precursors from remote regions, right? These are forcings from far away, all the way from the tropical Atlantic, Eastern Pacific into Western Pacific and Indian Ocean. This is much more closer, and these are further and further away. Of course, signal can also come the other way, and they do, right? So Fouché S2S obviously is capturing some precursors based on S2S from for a few weeks before. Obviously, modelers will now go back and see what in the SSTs could have worked to force rainfall extreme over Pakistan. Okay, there are many ideas on what happened, and there are already many papers written. Let's skip ahead to the discussion. The main point is clear, I hope, that Fouché S2S is beating ECMWF S2S, and it's got a new way of doing ensembles, which is very important because it's not an ML model that's just doing one realization. They have found a way to perturb and produce multiple realizations even within an ML framework, and looking at the longer lead forecasts that are more successful than ECMWF, they are able to see where the precursors are coming from and how the ML can identify such precursors. So let's read the discussion. In this paper, we introduced Fouché S2S, a machine learning based subseasonal forecast model. This model provides global forecasts of daily mean values for up to 42 days with a daily temporal resolution and 1.5 degree spatial resolution, encompassing 5 upper atmospheric variables across 13 pressure levels and 11 surface variables. The performance of Fouché S2S was rigorously evaluated against ERA5 reanalysis data and compared with ECMWF S2S reforecasts. So when you do historical simulations, you're going to do reforecast. A comprehensive suite of metrics was employed for this evaluation, including the deterministic metrics of the ensemble mean, the probabilistic metrics of the ensemble forecasts, and the capability to predict extreme events. The language is that if you have just one forecast, that's called deterministic. If you have a range of forecasts for ensembles, that's called probabilistic. So you have to compare both. and extreme events like the Pakistan floods. Our results demonstrated that Fushi S2S surpasses ECMWF S2S in forecast accuracy for the evaluated variables. Furthermore, Fushi S2S significantly improves accuracy in predicting the MJO, extending the skillful MJO prediction from 30 days to 36 days, as we saw the skill score. This improvement is particularly important given the MJO's influence on global climate patterns, and consequently, it improves the model's total precipitation forecast accuracy globally. Moreover, Fushi S2S has shown utility in practical scenarios, such as its superior performance in predicting the extreme rainfall during the 2022 Pakistan floods earlier than ECMWF S2S model. The early prediction capability is vital for improving disaster preparedness and response. So if you say we improved MJO forecast, that's a general statement, but if you do it for a particular event like the Pakistan floods, then you are showing actual skill. While Fushi S2S offers a computationally efficient and accurate alternative to conventional NWP models for seasonal forecasting, it also presents significant opportunities for improvement. Discussion is much longer. I've jumped to the end. For instance, the ECMWF S2S model runs at a spatial resolution of 36 kilometers, which is considerably finer than the 1.5 degree resolution of Fushi S2S. Currently, Fushi S2S predicts daily mean values up to 50 hectopascal in the atmosphere and lacks critical weather parameters such as daily maximum and minimum temperatures, which are essential for some applications like maybe heat waves or agriculture and so on. Furthermore, given the known discrepancies between the ERA 5 total precipitation data and the actual observations, GPCP observations have been utilized to evaluate TP forecast performance for both of ECMWF and Fushi forecasts. So you have to keep in mind that models always have deficiencies, and reanalysis themselves also have differences with observations because there are model biases that are obviously in the reanalysis as well. Anticipated future enhancements to the Fushi S2S model include increasing the spatial resolution from 1.5 to 0.25 degrees, incorporating additional weather parameters, extending the forecast beyond the current upper limit of 50 hectopascal, and employing more accurate TP data sources to enhance forecast accuracy. Okay, so just keep in mind that this is generally good news that we have to keep working with AIML. This is a train that has left the station in terms of them playing a part in the climate and weather forecast business at every time scale. Plus, even if dynamic models go to 1 kilometer resolution as being proposed by Tim Palmer and others, which I agree with, we will still need AI to analyze the output of a 1 kilometer resolution model, because that's going to spit out so much output that you cannot do conventional analysis with them. You will be using AI to do the analysis. Okay, so let's leave this here. I have one more podcast immediately following this in which I am involved, again, not as an AI person but a dynamic person, to show that the monsoon intraseasonal oscillations, another intraseasonal feature, can also be predicted with AI ML, and the lead time of prediction can be increased, as well as skillful forecasts can be improved over dynamic models. Okay, that's in the next podcast. See you.